start my recording, and then I should continue by sharing my screen. Can you see my screen? Can you see my screen? Yes. Okay, very good. So now we're all happy, and let's start. So last time, thinking of it, right? So we are basically still discussing vectors and tensors in curved space-time. Again, what we're up to right now, I mean, we want to be able to write down equations in physics that, in any arbitrary curved space-time. But what we are up to right now, to be even more precise, we are, I told you that there are two questions, right? One is, how do we describe the motion of particle in curved space? And this we already answered. This is the geodesic equation. And the second question is, how does the existence of mass or energy act to curve space-time? For that, we'll have to define what do we mean by a curved space-time, but we'll do that due time. So right now, what we're up to is to look at the generally, how do we describe physics in curved space-time? And really, we worked quite hard last time, but it was really more technical than anything else. Because what we did, I can summarize, we did just the thing which is called covariant derivative. Right. We say, as you know, that physics is full of equations that, partial differential equations. Pretty much, well, not all, but most equations in physics contain partial derivatives. And as we say, a partial derivative by itself, if you take a vector and you take the partial derivative of a vector, this is not a vectorial quantity. So it's not quite useful for us. So we were looking for a way of generalizing the concept of partial derivative into curved spaces. And then we looked at the transformation of the affine connection. I'm not going to repeat all this because there was a lot of algebra there, which, just following all the steps and hoping that you don't get lost with any of the indices. But the end result was quite important. The end result was that we were able to define the partial derivative of a vector, covariant derivative of a vector, which we defined by capital delta lambda v mu, or v mu semicolon lambda is just the regular partial derivative, dv mu over dx lambda, plus extra term for the affine connection, gamma mu lambda sigma v sigma, right? So for the affine connection, yeah.
Sorry, I had a question. So if we use that to describe derivatives in curved space-time, but on the other hand, the geodesic equation describes motion on curved space-time, why don't we use a covariant derivative in the geodesic equation?
I'm actually going to answer this exact question in a few minutes. So wait with this question for a few minutes. It's a very good question. You're right. You got a very good insight. So this is the covariant derivative of a vector. Then the covariant derivative of a covariant vector, right, would be beta lambda omega mu. Again, it's omega mu semicolon lambda would be d omega mu over dx lambda. But now, of course, we have a minus gamma. Again, the lambda and the mu will become dummy indices. And then, sorry, not the dummy indices, we'll just go to the affine connection. Sigma is the dummy index, omega sigma. And then the regular, covariant derivative of any tensor of any rank, you just have an extra term of plus gamma for any any upper index and an extra term of a minus gamma for any lower index. So for example, the covariant derivative of tensor T mu1, mu2, nu sigma, right, is just the first we have the partial derivative dt mu1, mu2, nu over dx sigma. And then we have a plus gamma. So the first index will go into the gamma, mu1, and then the index of the derivative will also go into the gamma, so that's a sigma, and then the third will be a dummy index. And then t, the first index that went into the gamma would now replace with the dummy index lambda, mu2, and nu, right? And then plus, of course, the same gamma, mu2, sigma, lambda, t, mu1, lambda, nu, and then a minus gamma. Now we'll have the dummy index will go up. And so the one of the indexes, the one that we are taking the derivative of, will go down to the gamma. So it will be a sigma, a nu, and then a sigma, and then t, mu1, mu2, lambda. It's actually quite easy to remember how it works. And of course, there is one term for each index. Right? So we have the partial derivative plus one term with the gamma, plus one term with the gamma, then a minus one, because we have three terms here.
שאלה ברשותך.
Yes.
למה מיו 1 ומיו 2? תמיד השתמשנו מיו ניו, מיו רו, מה זה מיו 1, מיו 2?
It doesn't, so the question is, why do I use mu1 and mu2 and not mu, nu, rho? You can do whatever you want, it's just a name. Okay. I just put the mu as an upper one and nu as a lower one. You don't like mu1 and mu2, you want to write instead rho?
Oh.
It's fine, I can put a rho here.
And even the mu1, you have to
then I have to
cancel the one.
Then I have to put the rho everywhere. It is just a notation.
Now then, okay, thank you.
If you prefer it like that, that's perfectly fine for my son. As long as you don't get confused.
Okay.
All right. Any more questions? No. Okay, and then we said, you know, that now we can use all the properties of the tensors, right? The linearity, the external direct product, the contraction, right? Remember we had the contraction. Did we speak about contraction? I think we did, right? T mu nu. I can take two indices and make them dummy, right? It's T nu rho, right? That's called a contraction. I think we discussed that. I hope I did. Okay. Or there is a sum over one upper and one lower index, right? And I can use that with the covariant derivative, and basically I'm quite happy because I got myself a prescription for taking an equation and knowing that it is, you know, going to be a true equation in general, right? Because again, the importance of covariant derivative is that, you know, twofold, right? One, it converts a tensor into a tensor. Right? Importance, a covariant derivative. Right? Terms that converts. So we stay with tensorial equations, which is quite important for us, right? Because then we can use the principle of general covariance, right? And second, it reduces to partial derivative in the absence of gravity, because in the absence of gravity, G mu nu turns into an eta mu nu, and all the gammas, all the affine connections become zero. So we end up just with the partial derivative term. So right? It reduces to ordinary partial derivative in the absence of gravity. Right? So flat space-time. So that gives us a prescription for writing down an equation which we know holds, right? So we take an equation which we write it in the framework of in the framework of special relativity, so we don't need gravity, right? So if we have an equation, we take an equation, prescription, right? We take an equation that we know holds in special relativity. Right. And then all we have to do with this equation is to, one, every time we have eta mu nu, replace it with a g mu nu. And every time we have a partial derivative, replace it with a covariant derivative. That's called the comma semicolon rule. Right? Partial derivative is replaced with a covariant derivative. And that's it. All right? So the resulting equation that we're going to get is generally covariant. It's true in the absence of gravity. So according to the principle of general covariance, it's going to be true in the presence of gravity as well. Plus, this also proves that we were not wasting our time studying special relativity. Because once we have something in special relativity, turning this equation into general relativity is very straightforward. Right? Cool, isn't it? Have to admit it's cool. It's just a matter of practice from here on, right? Once you practice it, you see it, it's straight away. I'm actually quite surprised because for me, normally when I write this derivative, it's kind of automatically write the comma semicolon. I'm glad I didn't write it. I think I didn't write it so far by mistake. Questions? Any questions? No? No question. Okay, if there are no questions, now I'm going to go back to the questions that I don't know, what's your name? That asked.
Done?
Done. Okay. So it gave you some more insight of what really is going on here. So it's called geometric interpretation of covariant derivatives. Okay. There is something which is actually very simple that illustrates what's really going on here. Let's start from the beginning. Let's say that we have flat space-time, and you want to take the derivative, right? So consider derivative of a vector in flat spacetime. Right, the simplest that you have. dv over dx. Right. What does it mean, dv over dx? Right. We take the limit, right? V at some point, right? X alpha plus dx alpha minus V at x alpha divided by dx alpha. Right? The limit dx alpha goes to 0. Right? That's what, this is the meaning of a derivative. Right? And I'm asking because this is something that I learned in high school, and I'm not sure that this is being taught in high school anymore for some reason. But you're familiar with that, right? Yeah? Yeah, okay. Let's draw it. What are we doing here? So we have a point in space, call this x alpha, right? And I have a vector. This is V at x alpha, right? And then I have another point, x alpha plus dx alpha. And I have another vector. This is V at x alpha plus dx alpha. Right? Now, have you noticed something interesting? These two vectors, they do not belong to the same tangent space, right? One of them belongs to the tangent space at x alpha, and the other one belongs to the tangent space at x alpha plus dx alpha. So it's a different point, right? So how can we subtract the vectors at the two different points? Well, the simple answer is we cannot, because they don't belong to the same space. They don't live in the same world. So what do we actually do, right? You never thought of it, I assume, maybe. You never thought of it like that. But what do we actually do when we try to do this subtraction, to take this derivative? Right? What we do is called a parallel transport. So we take this vector and we just transport it parallel to itself back to the point x alpha. Right? So this is V parallel at x alpha. And now, after we did that, now we can take the difference, which is this, right? Delta V. So nobody ever told it to you, I guess. But in reality, when you take this derivative, you're doing two operations. The first is that you take the vector and you parallel transport it. So transport it parallel to itself. It's not a big deal. It's Euclidean space, right? So it just stays there, not changing, right? And only after you transported it to the same location, that's the original one, then you can use the parallelogram rule to calculate the difference between these two vectors, right? Now there's no big deal. It's an infinitesimal displacement. The space is flat, you know, in Euclidean space. No issue. But the important thing to remember is that you did two operations, right? You first did a parallel transport. So parallel transport. We're going to touch that shortly. From x alpha plus dx alpha to x alpha, right? And then the second step is to subtract the original vector. Okay, so you really did two steps. You might not have thought of it like that, but that's what you did. Right? Now, what happens in curved spaces, right? You in fact do exactly the same, right? Remember, right, if you want to take the derivative or the difference between two vectors, you can only compare vectors that belong to the same space, right? You cannot compare apples with oranges, right? So, really in curved space, you also have to parallel transport. Now, there is no big deal. You can always do that because we said that the spaces we work on, you know, the manifolds, are well behaved. Namely, in the vicinity of every point, they look Euclidean, right? So if you go close enough, and what we do here, of course, we take the limit of dx alpha goes to 0. So when we're close enough to the point in question, right, x alpha or p or whatever you want, right, then you know, it looks like Euclidean. So we can always do this parallel transport. But now something, additional thing happens. And what is that? Is that during the parallel transport, during this first step, the coordinates of the vector change, right? Right. And this results from the change of the, you know, the angle the vector makes with the basis coordinates, because the basis coordinate change. The easiest way to think of it is just to look at flat space, but write it in polar coordinates, or even not write it, just draw it in polar coordinates. So let's make some drawing, right? So in curved space, during parallel transport, the coordinates of a vector change, right? I have a flat space, it's Euclidean space, but I draw it, I draw spherical coordinates. Now I have a vector. Right. This is a point x alpha plus dx alpha. Right. What are the coordinates of this vector? Well, this and this. Right. Now I take the vector and I parallel transport it. So I take it parallel to itself. Let's say I transport it here. To the point x alpha. Right? You see, the vector is parallel transported to itself. But now, since I'm using spherical polar coordinates, right? Now the coordinates of the vector have changed. Right? Now the real reason of what changed here, right, is the angle that the vector made, right, with the basis vectors. Right, I think you can see it from here, right? This is the angle, this is the angle. No, it's not the same angle. Although the vector has been parallel transported to itself. Right. Now this change, now I'm answering exactly the question, well, not yet, but I'm getting closer. This change, right, is first order, right? Because we're talking about infinitesimal changes, then it would be linear in the components of the vector, right? Then I should say this change is linear in the components of the vector. Right. So if it's linear, that means that we should get something when we take the derivative, right? That means that we should get something that look like d beta v alpha is just d v alpha over dx beta plus some extra term. I denoted with gamma bar, right? Which is linear, so it will be alpha, beta, gamma, v gamma. Right? So again, this term, we have two terms here, right? This term it represents the real change of the vector when it is shifted from x alpha to x alpha plus delta x alpha, right? This is a change in the vector field between points. Right. This term here is because of the change of the basis vectors between the 2 points. Are you all with me? Okay, you see that? This is something which is easy to visualize. As easy as it gets in this course. It's easy to visualize.
So the second term acts like a sort of a transformation on the vector from the old basis to the new?
Yes. Yes. Now I wrote it down similar to the affine connection. I put a bar just to ensure that this is not, to clarify, this is, at the moment, this is not the affine connection. It's just some linear term in V gamma, in V, right? But of course, this is identical to the affine connection. And of course, this is not a coincidence, right? And now I go back to your point, right? So this gamma is going to end up to be exactly the affine connection, right? Why? Because going back to your point, right? Look at the geodesic. What is a geodesic? So gamma bar is going to turn out to be equal to gamma y. So look at the geodesic. What is a geodesic? In Euclidean space, what is a geodesic in Euclidean space, in flat space?
Straight line.
The straight line, right? Essentially, this is the curve of minimal distance, right, between points. But I can think of a geodesic in a slightly different way, right? I can think of the geodesic as a curve in which the tangent vector to the curve is always parallel to itself, right? it is of straight line. But also a curve whose tangent vector is always parallel to itself. Right, again, I have here space, Euclidean space. I have 2 points, right? The geodesic, right, is a straight line between these 2 points, right? So this, we call it x alpha, and this doesn't matter, right? Now I can look at the tangent vector to the curve, right? And the tangent vector to a curve, right? U x alpha, right? Everywhere I go along the curve, right? So it would be x alpha prime, right? If I take that and I parallel transport the tangent vector along the curve, it's always going to be parallel to itself, right? U parallel of x alpha prime is just U of x alpha prime, right? I took the tangent vector at point x alpha, I parallel transported it, so transport it parallel to itself to another point along the geodesic, right? And it's parallel to itself. Right? So in fact, I can use this as an alternative definition to the geodesic, right? I can alternatively define a geodesic as a curve whose unit tangent vector is parallel to itself. Right, now you notice that this, so a curve whose tangent vector is always parallel to itself. This is an alternative definition. Of a geodesic. Right, it's pretty nice geometric definition. So if I call it U, that means that if I take the covariant derivative, right, of U in its own direction, then what must it be? Right, it's the covariant derivative of U in the covariant derivative of U in the direction of U. Right, the same direction. Remember that the vector U defines, you know, a path. Right. We said that vectors are directional derivatives, right? So what is that? Well, we said the covariant derivative. We just wrote it here, right? So let me just copy from here. Just U beta du beta over du alpha, sorry, over dx beta. Plus I said that there's this extra linear term, gamma, alpha beta gamma, u gamma. And this must be equal to 0. Right? But
where did the u beta come from?
Oh, just dx u alpha. It's just the derivative with respect to the direction of u, right? I can write it down as du over dx beta times dx beta over d tau or something. So u alpha or u beta is just dx beta over d tau.
I see, thank you.
Okay, but what do we know about the u? Right? What do we know about the vector u? What equation it must fulfill?
Geodesic equation?
Geodesic equation, right? Right? U fulfills the geodesic equation. Right? So I can write it down again as u beta du alpha over dx beta plus gamma, but now it's a real affine connection. Alpha beta gamma u gamma is equal to 0. So immediately we get that this linear term, gamma bar alpha beta gamma, must be equal to gamma to the affine connection. This pretty much answers your question, right? So in fact, this is a much more elegant way of defining a, the geodesic equation, or what is a geodesic, right? I can say that geodesic is a curve whose tangent vector u obeys what is written here. So a geodesic is a curve whose tangent vector u obeys u is equal to 0. It's a very elegant way. Right? You see where it all comes, right? The geodesic is simply a curve, a straight line, or the shortest path, right? Is a curve whose tangent vector is always parallel to itself, right? I could do another curve, which is not a geodesic, right? And then when I draw a tangent vector at this point here and a tangent vector at this point here, they're not going to be parallel to each other, right? As opposed to the geodesic. Only along the geodesic, a tangent vector is always going to be parallel to itself. Right? This is.
So basically, the geodesic equation is just a way to say the maxima of a covariant derivative.
Why maxima? A minima, 0.
Or a minima, yeah.
Yeah, the same way as we said, okay, this is the path of shortest time. Right, this is the shortest time it takes to reach from point A to point B. So another way of saying, okay, this is the path that if I take the tangent vector to the path or to the curve, at each point, it's always going to be parallel to itself, right? An airplane flies straight, it's not doing rounds. Yeah? Now it's clear? Some visualization, or just makes you more confused?
Saf?
Yes.
Can you give maybe a visualization of the great circle? Because each tangent vector is changing, right?
No.
Along the curve.
No.
Why not?
Why not? Because you are restricted to 2 dimensions. You need to think of it in terms of your subject. It's not what may confuse you is that you may think of it in terms of 2-dimensional surface which is embedded in a 3-dimensional space. But this is not the way to think of it. you are forced to move along this curved space, right? The shortest path from Tel Aviv to New York goes by digging down a hole through the earth, right? Of course, we cannot do that because it's not practical. So we take airplanes that move along the surface of the earth. But when you are along the surface of the earth, the tangent vector is parallel to itself along the surface. It is subject on the surface.
It looks like projections.
Yeah, because you are thinking of that in terms of 3D, but forget about the 3D. Think of it now. You cannot live. You don't even know that the Earth is spherical. I'm just asking you, what is the shortest path from here to New York? And you say, oh, I go there. I don't know, 10,000 kilometers, and I get to New York.
Yes,
and
from
you
the
just
point
go
of
on
view.
there. You just go on straight over there, 10,000 kilometers, you end up in New York.
Yeah, but from the
like
point of view,
where I am, but it doesn't matter, right?
what I'm saying, it's from the point of view of an ant. Yes, I agree, but from the point of view of an outside observer, it looks.
That's what we are. We are ants. We are stuck to the manifold. We are ants. Of course, I'm giving you all these examples in 2D because it's easy to think of it in 2D, right? Not in 3D and not in 4D, right? We are ants. We cannot get outside. You think in terms of astronauts that can leave the surface of Earth. The one who really derived it first was Gauss in the 19th century, and at his time there were no astronauts, and in Einstein's time there were no astronauts. But again, if you get confused, we will discuss in a few weeks' time the cosmology and the cosmos, right? Even if you can imagine getting out of the surface of the Earth to the moon or to Mars, you cannot get outside of the cosmos. You cannot go outside of the universe and ask yourself, oh, I can see that the universe is embedded in a bigger dimensional space or something. That you cannot do. You have to be stuck to what you have. Right? So if I go, I'm forced to live on the surface of the Earth. And if I want to go the shortest path to New York, I go there, straight line. And I carry with me my vector or a stick, and I just go on straight, 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 straight. I'm not going not left, not right. I'm just going straight. And I'll get there the shortest path. So it's always parallel to itself, subject to the fact that the surface of the Earth is round.
So I can imagine parallel by just saying, okay, like Yahu said, so I'm a little ant who's I carry an arrow on my back and go on the line, and then whichever direction the line it is, it's parallel to my path. Like it's parallel to itself, not to my path, it's tangent to my path.
Exactly. This is the right way of thinking of it. We are all ants in a big universe. That's what we are.
Thanks.
Okay. Some ants are smarter than others, so they can think of these things. But yes, that's what we are. Okay. Good. More questions? More questions? Okay. So, kind of to end up this part, without going into the details, let me show you that what we learn here is a generalization of several things which you actually know quite well from other courses. But again, you might not have fully thought of it in this way. So what I want to do, finish up, let's talk about gradient, divergence, and curl. Right. Now, of course, you've seen all these, right? You learned that in first year. You learned this? Yeah, right? Yeah, okay. So we know what they're very useful many useful equations for, electromagnetism and fluid mechanics and many other areas of classical and quantum physics as well. We need to have a three-dimensional vector calculus, right? Which means that we need functions such as gradient and divergence and curl and all this. Laplacian as well there is. So I'm sure that you have seen how to write down these equations in non-Cartesian coordinates, right? I'm sure that you've been taught about cylindrical coordinates and spherical coordinates. Am I right? Yes. Okay. So this is not new to you, I hope. So what you're really told I won't surprise you now if I tell you that what you were told are really specific cases of the most general derivations, which you actually did right here, right? By using what we just learned, you can actually derive these for any set of coordinates that you like, not necessarily the ones that you were taught on first year or second year, whenever you're talking. So, for example, what is the covariant derivative of a scalar function? If I take a scalar, take the covariant derivative, what is that?
Just a partial derivative, no?
Yeah, exactly. This is just the ordinary gradient, right? This is just the ds over dx mu. And what is dx over dx mu? This is just a gradient. Right? Another very simple special case, the curl. Right? Curl. If I think of the curl of a covariant vector, right? Remember, I have omega mu. It's covariant vector. The curl, so omega mu semicolon nu, right? It's just the omega mu over dx nu minus gamma lambda mu mu omega lambda, right? Now, gamma is symmetric. So what is a curl? Omega mu mu minus omega mu mu. This is a curl. So this ends up with just the ordinary curl, right? The omega mu over dx nu minus the omega mu over dx mu. Actually pretty nice because everything you get like pretty straightforward. What about the divergence? Divergence is slightly more tricky. Right. So if I take the covariant divergence, is V mu mu. This is the covariant divergence, which is just d V mu over dx mu plus gamma mu mu lambda V lambda. Just on the safe side, after we finish, go back to your one of your first or second year's textbook and see that you recall what is a divergence. Now we do a little bit of a trick, right? And the trick is that now I can use the definition that we had and the symmetric part. So gamma mu mu lambda, right, is just 1/2 g mu rho, and then d g mu rho over dx lambda plus d g rho lambda over dx mu minus the g mu lambda over dx rho, which, using the symmetric part of g mu and rho, that means that mu and rho, so this term and this term will cancel out. So we're left with 1/2 g mu rho, the g rho mu, so it doesn't matter dx lambda. And then I'm going to use an identity which I can ask you to prove, or I can prove it for you later on. Not a trivial identity, but it's doable identity. I don't know which textbook I took it from. If you have a matrix M, trace of M minus 1 x times p over dx lambda M of x is d over dx lambda of ln of the determinant of M. M can be a function of x. This is a mathematical identity which I'm using. And of course, for the matrix M, I'm going to choose G mu rho, mu rho mu, and that gives me gamma mu lambda to be 1 over square root of G d over dx mu square root of G, the determinant. And so with that, I can use the covariant divergence of a covariant contravariant vector v mu mu is 1 over square root of G d over dx mu, and then square root of G v mu. Now I leave it to you as an exercise to calculate that in your favorite coordinate, non-Cartesian coordinates, and plug in the spherical coordinate or cylindrical coordinate or whatever you want, and see that what you get is exactly identical to what you got for divergence in these coordinates. Okay, and that also leads us to the covariant form of Gauss theorem. So for Gauss theorem, covariant form of Gauss theorem. Right. V mu 0 at infinity. Then we have that integral over space d for x square root of G. V mu is equal to 0. A lot of these theorems from vector calculus that you learn, you're going to get a very simple form like them. Okay. By the way, you might remember this is an invariant volume element. Now, finally, right, when we spoke in 3D, which you did, right, Laplacian of a scalar function is just the divergence of the gradient. Okay, 3D, Laplacian. Divergence of gradient. And the squared S is just G. I'm going to use now IJ because it's just 3D. So I can use Latin in that sense. Then S, I, so my column J. If you want to write it down explicitly, this 1 over square root of G, D over dxj, square root of G, Gij, ds or dxi. So really you can develop the entire vector calculus in any arbitrarily general coordinates, which should not really surprise you because well, that's what we're doing all along, generalizing the concepts of flat space-time into any arbitrary general coordinates. Okay, questions?
Yes, I have a question. Should we remember, should we know how to work with all this? Because in the homework, we have something with the determinant, and the determinant, I didn't know what to do with it because it's just a determinant. It's not like something that you can do a lot. So I use something like the formula you just showed after a long search in Google. Via the joint metrics, and then I got something which the derivative can give you something, but I don't know. I wouldn't know how to do it like in general.
Well, I just showed you how to do it in general. I'm not sure what you're referring to exactly right now. And rather than a longer search in Google, you could have a shorter search in one of the textbooks that I recommended. You'll get the same result, I guess. I don't know, it's something which is very useful if you for the right problems. So I'm not sure if you need to memorize that. I don't know.
No, because there isn't any other way to use the determinant, right? Because we don't have any connection between the determinant to anything else, just the determinant.
Well, I would say the following. There is a general description which is here, but practically, the metrics that we're going to use in this course are actually quite simple, like relatively simple. Okay. Right now, the only metric that what we talked about is the Minkowski metric, right? And then the other things are semi-trivial, naming meaning taking either the flat metric in written in different coordinate system. So from which you should be able to derive the metric. And I think I asked you in one of the problem sets to write down the metric at the surface of a sphere. So this is really a two-dimensional metric. So it's slightly more complicated. Maybe it's not more complicated, actually. It's simpler because it's only 2 dimensions. It's just not equivalent to a flat metric because a sphere is not equivalent to Euclidean space. But really the metrics that we will have to use in practice in this course are relatively simple metrics. We're not going to use any complicated, mathematicians can invent all sorts of crazy metrics that they have in mind. But as physicists, we care, we want to make the world simple. So we want to use the simple, the simplest there is. So I'm not sure exactly what you got stuck with, but the equations are derived. That's my job, right? To show you the equations in the most general form. And the practice is to take this general form and write down, solve it for a specific example, which is going to be much more simple than not going to be particularly complicated.
Okay.
Does that answer your question?
Yeah, I hope. Yeah, I hope.
Okay. I wouldn't be too worried about it. If it comes to that, normally in exams, I don't expect you to memorize hard equations or to be very small. I expect you more to show that you understand things. Now I will ask, of course, in the exam, I do ask questions that show that you have to solve something. But when I look at the exam, I'm trying to figure out whether if you got stuck on something, whether you got stuck because you don't understand it, you got stuck because you forgot something, or you got stuck because I don't know, you copied in your homework. And I see, you get
What's up? Oh no, he's gone.
In the middle of getting stuck is that stuck. Okay.
Sometimes not obliged to that, but I tend to take questions from homework and put them in the exam sometimes. Or one question, for example. So think of it next time you're working on your homework. If you choose to do it by yourself or you choose not to do it by yourself. Just let me know. And I'm not obliged to that, so I don't know. I don't have anything in my mind about what I'm going to put in the exam this year. So. But my general approach is, especially in this course, I'm not looking for you to, have very complicated derivatives. Because, writing down the equations, you can always find them in textbooks. Whether you understand what the equation means and when it is possible to use it is a completely different question. And that's what I'm looking for you to show that you understand. Okay. Yes.
I have a question of the first Laplacian. Why does it have a, can you maybe say the indices? Because it looks like a tensor.
3D. So it's just a 3D Laplacian, right, that you derived in 3D. It's not a 4D. You can do a Laplacian in 4D. I think I asked it in one of the questions. Then it's called a D'Alembertian. A 3D, you just have, remember we spoke about that with the indices. We say that we use Greek indices when we do 4 vectors. So when we work in 4-dimensional space.
Yes, yes. I'm talking about we do a summation of I and j, and you write I and j outside the brackets.
No, this is a semicolon.
It's semicolon. Oh, oops.
Semicolon, and this is a semicolon.
Okay, sorry.
The derivative of s with respect to I, multiplied by gij, and then I take the derivative of all that with respect to j. It's a much more elegant. Okay, what do you say? Shall we go on to the next topic, or shall I stop here and use the next half an hour or so to give you a short tutorial? I think in 25 minutes, it's maybe best that I'll give a short tutorial, which means that I'll likely not give you the problem set today, but I'll wait until Thursday to give you the next problem set.
Can I just ask one last question before we move on?
Yeah.
Why, when you define the Laplacian, why did you multiply the s with the metric? I didn't quite get that.
Oh, because this is the divergence of the gradient. I just use what this is the gradient. I wrote it down here. And this is the divergence. This is the divergence. I just use this equation here. So I had this gij here.
I'll ask you after the class. I don't quite see it yet.
Okay, well, work on it. We'll see. Okay, so let me give you a quick derivation. So, okay, you know what? I use this equation, which is non-trivial. I have it in my notebooks. I'll post my notebooks today so you can read all the, you can read it, so you can go through the mathematical proof of it. Let me go in the next 20 minutes to give you the precise definition of a manifold. So just to clear up this point. So a manifold. I told you the way to remember it is the right way the simplest way. A manifold is a space which locally looks Euclidean, but globally is not. And that's enough for any practical purpose that we have. But there is, of course, a mathematical definition, and the importance of the mathematical definition, and I guess that's the thing that can be quite tricky, is how to define such a space without making any higher dimensional spaces that it may be embedded in. So I do not want to use anything out external to this space. I would like to define a manifold in such a way that uses only things that exist inside of it. And again, this is a bit, we're going back to this example of the ants, right? I want to know as an ant, I don't have a way of leaving my space, and I want to know to be able to describe my space without leaving it. And so I'm not an astronaut that can look at the Earth from the outside and say, oh, I can see it's actually round. No, I want to be able to do it without leaving Earth. And of course, the logic is I want to do it without if I want to discuss cosmology, I cannot leave my universe. The technology for that does not exist and likely would never exist. So I cannot leave my universe and look at it from the outside. So what is the exact mathematical definition of a manifold? So I said that roughly it is n-dimensional space that locally looks Euclidean, but globally is not. And the classical example is the surface of the Earth, right? Wherever you're sitting right now, whether in the classroom or in home, right? If you look around you, the floor is flat, but it really isn't flat, right? So to be more precise, what we are interested in is what called differential manifold, which are fundamental concepts in math. So what we have is a differential manifold. Okay, so before I can give you the precise mathematical definition, we need to go through a set of other definitions just to make sure that we all speak in the same, on the same language. So the first definition is what's called a map. Definition is what's called a mapping. So we have two sets, right? By the way, I believe some of that you might have seen in calculus, Infi. I assume everybody took calculus 1 and 2. Yes, 3 and no, maybe. Let me guess. You took it, but you're not sure that you remember or you fully understood what was in there. I know. It's one of the hardest, and it takes a while to do. I can help you. After you do enough general relativity, calculus looks actually quite simple in some sense. I know it's really helpful. So, okay. That's the reason why if you remember that, that's enough. Okay, the rest is for those of you who love calculus and want to do the exact definitions. It actually, after you think of it, it's not that bad. But I can say the same about calculus. After you think of it enough, it's not that bad. Okay, so a map between two sets. So I'm giving two sets, right? M and N. So given two sets, M and N, right? So I have a map phi between M and N. Right? This is a relationship that assigns for each element of M exactly one element of N, right? This is the generalization of what we call functions, right? So M is a set. Remember, mathematics is all about sets. It's not even about numbers, but that's the interesting thing about maths, right? And a map is what we call the function, is something that for each element of M provides a relationship between each element of M, right? A map is a relationship that signs for each element of M and exactly one element of N. That's what we call a function, right? Now we can think of a composition of maps. Right? So if we have two maps, phi from A to B and psi from B to C, right? Then the composition will be psi of phi, which takes course, from A to C, right? Which is just defined, by psi dot phi that operates on A, where A is an element in A, right? It's just psi of phi of A, right? A is an element of A. Right? So again, this is the set A, this is the set B, this is the set C, right? So phi takes me from taking A element of A into an element of B, psi take an element of B into an element of C, and psi operating on phi takes an element in A and into an element of C. Right? It's not even confusing at this point, I hope. Maybe it's likely. Okay. Then we have the definition, of course. If we have a map phi between M and N, right? It's called a one-to-one, 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 which should be one-to-one. It's a precise definition. One-to-one, חד-חד ערכי, right? If each element of N has exactly or maximum one element of M mapped into it. Onto al, right? Each element of N has at least one element of M mapped into it. Right? So, for example, if I have phi from R to R, right? You can write phi of X is e to the power X, right? This is a one-to-one mapping on חד-חד ערכי, but it's not onto, right? Because there are elements in R which do not get any function that gets into them, onto them. Yeah? Map that is both one-to-one and onto, we call how do you call maps that are both one-to-one and onto?
Invertible?
Yes. These are invertible maps. Now, given a map, so given a map phi, then the set M is called the domain. תחום, בעברית, תחום של הפונקציה. The set M is the domain of phi. How do we call the set of points in N that M maps onto? How do we call those?
Picture?
Image.
Image.
Actually, you're learning linear algebra. Right? It's not even calculus, it's linear algebra. Yeah? It's easier. Now, what we call smoothness of a function. Smoothness. Right, this is the number of derivatives that that are continuous. Right? This is the number of continuous derivative it has. Right. So if we have a map, for example, phi from Rm to Rn, right? Example. So it takes n numbers, we call tuples because these are ordered numbers. So it takes m tuple. So it takes, takes, so it's m tuple. That is the, not sure what is the Hebrew word for that. So x1 to xm and maps them into y1, yn, into an m tuple. So you can think of it as a yi is just a phi I of x1, xm. Right. Now, if the p's derivative of each of these functions exists, then we call this function a CP. If the p derivative exists and continues of each function exists and continues, we refer to the function as CP. That's how we call it. And if this is for all functions, then we say it's C infinity. Right? Sorry, if it's for all functions, then the map itself is CP, right? If this is true to all functions, then we call it phi Rm to Rn is CP. That's how we call it. And if we have maps that are C infinity, then we call them smooth. And it sounds abstract, but when you think of it, that just means that we're using nicely behaved functions, nicely behaved that, we can draw them as simple simple functions, no spikes, no corners, no nothing that looks bad. So most functions, but generally all functions that we will have in this course are going to be smooth. But mathematically, they don't have to be. Now, the last thing we need is that two sets, M and N, are called diffeomorphic if there is a C infinity map from M to N with the inverse. Right? M and N are diffeomorphic if there exists a C infinity map phi from M to N with C infinity inverse phi minus 1 from n to n. And the map phi is called diffeomorphism. So did you encounter this concept of diffeomorphism between two sets? No? I'm sure you heard you've heard the word diffeomorphism. Have you? It's not the first time you hear this word. So this is what it means. Diffeomorphism, I have two sets, and there exists a map which is continuous, nicely smooth, and it also has an inverse, which necessarily means it has to be 1, 1, and onto. Essentially, that means I have two sets. I can map one element in that set to one element in that set, and I do it in a smooth enough way. Most functions that we encounter do that. The ones that don't do that are nasty, ugly, and we call mathematicians for help. Or we just avoid them because they're not physical. So essentially what we have is that there is an invertible function that maps one differentiable manifold to another one. So such that there is the function is smooth and the inverse is smooth. That's what it means. These are all mathematical ways of saying we're just dealing with nicely behaved functions. We don't deal with any spikes, any corners, anything that is ugly and nasty. We leave this aside. Okay. Now we can take that and we can apply that to a manifold. So before we can do that, again, I need to have a few extra definitions, but now it's going to be quite simple. So the first thing is what's called an open ball. So one open ball, right? It's a set of all points x in Rn such that they are smaller than some radius r from some point y. So a set of all points x belong to Rn such that x minus y is smaller than r. What's up to her? Okay, it has no boundary, it's open. Okay, for y belong to Rn and r belongs to r. Okay, open ball, it does not have boundaries. Open set in Rn is a set which is constructed from arbitrary number. It could be infinite number of unification of open balls. Here's a set constructed from arbitrary, can be infinite. Union of open balls. Right. So for every point inside an open set, I can always find an open ball next to surrounding it. Okay. Is this the way? I think that you might have seen that, right? In your calculus or info. Have you seen that in your calculus or not? Or you're not sure?
We have seen that.
You've never seen that. That's one of the way of defining things there, right? You want to what's up to open sets. You've seen?
We've seen that in calculus 3.
Okay, so that's calculus 3. That's what it is, right? It has no boundary, essentially. Now I'm going to surprise you, right? what I call a chart. The other name of a chart is a coordinate system. Chart or coordinate system. Right? It's a subset U, is a subset U of the set M, along with a one-to-one mapping right, phi from U to R or Rn, such that the image phi of U is open in Rn. Right? Now, since any map is onto the image, then it means that it's invertible. It's a one-to-one. So U must be an open set in M. So again, remember what I told you. You have a space. I want to put coordinates. I can think of a coordinates as really setting functions, right? Oh, sorry, setting a map from a point in that space to a set in Rn. That's exactly what's written here. So I have a space here. This is my space. I have a point, P. Now, when I put a set of coordinates, what do? I do a mapping of this point P. So this is, you know, X and Y. Right, so putting a coordinates is nothing but setting a map between the point P in the space to Rn. That's exactly what's written here. This is what a coordinate really is. It's true in Euclidean space and it's true in any space. It's just a mapping between the point in space into Rn. But you know, it's a one-to-one mapping such that the image is an open set. That's actually quite important. But I won't have time now to explain exactly why it's important. But sorry. I have a set M, I have a subset U, and I have a mapping phi right, to Rn. And there's the image here. This is phi of U, which is open. Actually, I should draw it dry properly. To draw an open set, normally you draw with a dashed line. So again, think of it at home a little bit. This is exactly what the coordinate is. I just gave you here the explanation. This is what the coordinate here. Here I gave the explanation. This is what the coordinate really is. It's just a mapping phi from a point in space into, I give it a set of numbers. So now I know that this point is assigned with a set of numbers. Right? Yeah? Okay, think of it, it's a bit abstract. Two more things to go. So, what we call an atlas or a C-infinity atlas, right? It's an indexed collection of charts. Is an indexed collection of charts U, A, and phi A, which, right, the union is equal to M. In other words, it covers all M. U, A covers. And they are smoothly sewn together, right? So I can put one chart here, right? And another chart here, and another chart here, and another chart here, right? They all have to cover M, essentially, to make it an atlas, right? But it also has to be smoothly sewn together. Which means, what I mean by smoothly, it means that when they overlap, namely, if I have UA and UB is not an empty set, right? Then there is a map. The map is then and the map phi A plus phi B vector -1, right, takes a point in Rn, right, phi B UA UB, where it belongs to Rn, onto an open set phi A UA and UB into Rm, where all maps are C infinity. Basically, what I say, I can put coordinate system in location here and another coordinate system location here, but they have to be smoothly connected to each other. So if I have a point, say I'm using this guy over here, and so it will be mapping into this. And that means that this point here, which is the overlap point, is well behaved, essentially. I go it again in the wrong way.
What do you mean by well behaved?
Again, the mathematical definition is that I can take a function phi b -1 to phi a. So basically, I take the function back here to phi b -1, and then I take it back to phi a, right? And it maps onto an open set on Rn, basically. Okay. Essentially, it means that you can, going beyond all these abstract definitions, what it really means is that you know, if you define, let's say that this is my space, so I can define the coordinate set here, right? And I can define a second coordinate set here, and the points will be well behaved, you know, not jumping all over. There's a smooth connection in the region when they are defined. It's basically a system of charts, system of coordinate systems, which are related on the overlap. Now, finally, right? So now come the punchline, right? A C infinity and dimensional manifold is a set M along with a maximal atlas. So one that contains all possible compatible charts. Possible compatible. Okay, you have to digest it. It's not something that if this is the first time you see it, I'd be surprised if you get everything right away. But once you sit down quietly and you think for yourself, this is the way to do it. This is exactly how you do these things. The important here is that I do not need, the only thing I did was mapping between the space, the manifold M, and Rn. I just did mapping back and forth. And so I do not need to use anything external to the manifold to define it. Right? One more thing is that I use always open sets. So for example, if I have a closed circle, it's something like that. This is just a circle, right? It's not the space, just a circle. I call it S1. This is the way it's called, right? So I can think of a coordinate system, right? Of course, it's a one-dimensional. So I can think of it as a theta would be my coordinate. Right? So theta would be the coordinate system, which takes from S1 to R. Right? Now, the problem with that, I cannot do it like that because the open set, the image of theta have to be an open set. So we must exclude this point because this is not an open set. So let's exclude theta equal to 0 and 2 pi. That pretty much destroys it. So I have to actually use two sets if I want to, at least two charts if I want to cover S1. But S1 is a good enough manifold. Okay, I want to avoid this, double definition. I want to have a one-to-one correspondence. I cannot say theta equal to 0 and 2 pi. They cannot correspond to the same point. What I can do like theta 1, which will be defined from here to here, and theta 2, which will be defined over this region. And that's perfectly fine. Then I can cover the entire S1 in a smooth way, no problems. All right, think of it a little bit. I'll see if I want to give you the homework today. If not, that will wait until Thursday. I will post my lecture notes so you can review that. Again, this is a mathematical appendix. Those of you who like this math and you want to have the exact definition, I just gave them to you. Those of you who feel this might be too much of a math, then it's fine. I told you, for me, as long as you remember that, and you know what to do with it, then that's perfectly fine. The rest is just the math for what those of you who are interested in how exactly are these things being done. This is the exact way of these things, but this is what I just circled in red. This is from a physicist point of view, this is the important thing to remember. Everything else is for fun. All right. But also to show you that I'm not, it's not really, I think I told you, but can do general relativity. Some people do it in a hand waving way, but then it will be a hand waving. Or you do it properly. If you want to do it properly, really properly, then we have to go through that. I'm trying to do it properly enough so that you see that it's not really hand waving. Everything here is very, very solid. Okay. Any further questions? Oh. Okay. Well, on the good side, you see by now it's quite deep. On the other good side, there will be a little bit more mass to go, but we're starting to get close to the physics. We're doing hardcore math, and then we'll go to do hardcore physics. And we're starting to getting, we have something like 2 more weeks of hardcore math, maybe slightly less, but of the order of 2 more weeks, one to 2 more weeks. And then it will be hardcore physics, which will be as exciting or even more exciting, depending on your personal preferences. All right, guys, have a great rest of the day. If you have any questions, don't hesitate to ask. Send me an email if you're afraid of asking them or you don't want to ask them right now. I'll try to answer. All right.
Thank you.
Okay.
Bye-bye. Have a good day.
Yeah, have a good day.
Good day.
I'm recording.